Okay, so what do we have? Learning rate, right? These are the
Hmm.
number of epochs, right?
Hmm.
Activation functions, right? As you talked, tan, sigmoid, ReLU, and linear, right?
Yep, yep.
And there is no optimizer. Optimizers are just like what? That they just optimizers are what? Like they help the model to to like it adjusts the speeds, right? Optimizer
Optimizers are
adjusts
the
the
actually called the catalyst kind of thing, right? So they're
yes,
yeah,
where to
yeah,
move fast and where to move slow. That's it.
yeah, yeah.
Like in a saddle point situation, right? The model gets confused in which direction they should go, right?
Hmm.
So
Hmm.
there is Adam, right? Adaptive momentum.
Adam, yeah. Adam is very common. Yeah.
Yes. Similarly, in the activation function, ReLU is there, right?
Yeah. Yeah.
Okay. So, like in Adam, in case of Adam, it is adaptive momentum, and momentum is what? It just calculates in which speed, at what speed, and in which direction it should go, right? Similarly, we have Adagrad, right?
No, I have
Momentum of
not heard
Adam.
Adam.
Ah, yeah,
Yeah.
these are very old ones. Like the now currently most of the scenarios we are using activation function is ReLU, and in the optimizer it is Adam, right?
No, yeah.
So
Those
those
are
work best for most of the scenarios.
yeah. Yeah.
Okay. So we have a problem here. Do you see the problem that it is the binary classification, right?
Yeah. Yeah.
Problem type is classification, right?
Hmm.
We
Hmm.
have two classes, so it becomes binary classification, right?
Yeah.
We have some data, right? Two inputs, right? And
Hmm.
as you can see, these are the inputs. So if we each one with the next layer, these are the hidden layers, right? And it is the
Hmm.
output layer. But it also gets updated. So these comes under the hidden layer only, right?
Huh.
Each connection with the neuron from one layer to another would be considered as a weight, right?
Okay. Yeah. Yeah.
If I just add some neural network layers, okay, right?
Yeah.
Let me just do one thing. It will be very good, and you'll just like it. Uh, it will be very clear for you. If I just go plot uh, graphs, right?
Hmm.
We have Desmos, right? Okay. So
Weight means actually what got passed from one layer to another, right? That is
yeah,
called weight, right? Yeah.
yes. The actually, if we talk about neurons, right? In
Mm-hmm.
terms of human anatomy, right? What are
Hmm.
neurons? Neurons are just individual sort of gates, right? A
Yeah.
gate, and
Passing
Zog,
the
right?
information from one gate to another. Yeah, you are right.
Yes. So we just take it as a gate, right? And combination of gates can compute a very logical reasoning as well, right?
Mm-hmm.
So those are just gates. Suppose in this scenario, if we talk about this, suppose this is something or right, and this with this one is and. So we have a logical, combination, and it
Mm-hmm.
is able to capture what a particular reasoning. Suppose this is the input, and if I have to reduce the output, I need to traverse through 1, 2, 3, 1, and 2, right? Suppose
Yeah.
a different kind of input comes in, right? Then I need to traverse through 1, 4, 1, 1, 2, right?
Yeah.
Different
Yeah.
combination of logics. And what does it have different? The weights. And now let me just help you with that. Like how can we just make it understand easily, right? Y
Yeah.
is equal to 4x plus 3. Let's say this, or just
Mm-hmm.
reduce it, right? Okay, let's take this example, right? So this is a linear line, right?
Yeah.
Right. So if suppose we are having some data points, right? In machine learning. So before that, what I'll do is this. I'll just plot some points. let's say 0, 0, comma 2, okay, 0 or 1, comma 3, right?
Yeah.
And 2, comma 5, right? Something like this.
Yeah.
And we will be having more points like that, right?
Yeah.
And now we have a column, right? This is, suppose this is the independent variable values, right? In the machine
Mm-hmm.
learning. And this is what? A y, independent variable, right?
Yeah. Y-axis and
The x
x-axis.
and this
Mm.
is the y, right?
Yeah. Yeah.
So for machine learning, what does it understand? It just tries to just predict a line, right? It tries to predict a line which will satisfy most of the data points, right?
Mm-hmm.
It will
Mm-hmm.
satisfy most of the data points in such a way that if you just try to, right? If you just try to draw a line or just get calculate the distance between the predicted line and the point, it will give minimum loss.
Yeah. It should cover most of the points,
Most of
right?
the
That's
points.
what. Yeah.
Yes,
That's
that
we
is the
call
end
it
goal,
in the
right?
statistics, right? Yeah. Yeah.
So in this part, it will give loss a bit loss, and in this point as well, it will give a bit loss. But it is
Yes. Yes.
overall it is performing very well, right?
Yeah. Yeah.
But what happens in case of deep learning, right? This is a linear relation, right? Y is equal to
Mhm.
x plus 3, right?
Yeah.
But
Yeah. Straight
in
line
here,
equation.
in here, it becomes very complex. If we say x multiplied with this, then x, it becomes exponential, right?
Yep.
It becomes a very high degree polynomial equation.
Mm-hmm.
High degree polynomial, we cannot even imagine how will it look like, right? If it is
Mm-hmm.
x to the power 24 plus uh, 14x cube or 14x to the power 9, right? Something like that. How will we
Mm.
even imagine what would be the dimension of
Yeah.
that?
It is very difficult to predict that how close it is going. Yeah. You are right. Yeah.
Even if we can like get the dimension working in the mathematical verse, right? In the mathematical universe, but we won't be able to see the dimension because we cannot see more than 3 dimension, right?
Yeah. Yeah.
We are not able, we cannot visualize that dimension.
Yeah. And just one question I forgot that. So the number of actually hidden layers that we can choose, right?
Yes.
Yeah. So we can choose that. Okay, in my analysis or my prediction, I should use this many layer of hidden layers,
Yeah.
right? We.
There is actually a sort of like hit and trial method only works in deep learning most of the time, right? Get an
Mm-hmm.
estimate like how much hidden layer would be sufficient for such a problem, right? Because
Yeah.
in
So
deep learning,
yeah. So that's what really happens. So that's what actually all those finance or other companies, they don't go to that much. They don't allow us to go for the deep learning. Actually, if that the data is not that complex, they told way try to solve it in machine learning so we can
yeah,
have a actual human
financial data
prediction
is actually
also.
relational, right? It is linear,
Yeah,
so it is
yeah,
good.
linear. And it is very actually predictable. We don't have that
Yeah,
complex scenario
yeah. That
that you can always
complexity
go to
doesn't
deep
come with
learning.
that. Yeah, you're true.
Yeah, yeah. So
Because
in your company or your experience, do you
yes.
actually use the deep learning day to day basis?
No, I have just like worked on it, worked on deep learning architecture just to get a very good understanding of how actually it is working under the hood.
Okay.
So yes, so that was my only goal. So I have worked on machine learning. Then I just moved to deep learning. Why deep learning was actually needed in the first place, right?
To understand the concepts and
Yes,
why the laws
yes,
and
and
also for
why?
your use, right? Yeah.
Yes,
Mhm.
and when to use it, and how does CNN use deep learning, right? All these things.
Yeah. Yes. 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 You are right. Yeah.
And actually, I'm working on mostly on the data part and working on the agentic AI part only.
Oh, okay. Got it. Yeah. So then similar to me actually, mostly into the data and make it ready for
Yeah.
the team to run the agentic AI. Okay. Got it. Mm.
Let's see. Let's start with two hidden layers, right? And we'll
Mhm.
just do it 2 because we are having only two classes, right? So
Mm-hmm.
in the output, it would be better, right? And learning
Yeah.
rate is 0.03. Let's make it zero point 0.1, right? And let's
Mm-hmm.
see the training loss. The training loss for this, let's see. See, it got trained very easily, right? See, it got almost got what?
How
Training
many
loss became
epochs?
zero.
Yeah, yeah.
That means it got fully converged. If we just look at the weight, it is -4, it is 2. And if we just look at the weight, they are not changing at all, right?
Hmm.
They're not changing because the back propagation has happened already in a very good amount of like in a very less amount of time. Let's see how fast does it get like how much time does it take to just get
I
converged?
can see some losses. Yeah.
Yeah, it is 1.4, right? And this
Hmm.
is -3.8, right?
Yeah.
Because the data patterns, like suppose in the first iteration, this was the first data point it chose, right?
Mm-hmm.
And this was the second data point. And
Hmm.
this was the third one, or this was the fourth one, or this was the fourth one, fifth one, sixth one. So the choice of data also affects the weights and biases, right? But
Hmm.
training loss actually converges and gives you that okay, whatever you have, because the end goal is not what is actually the to capture the relation. It is not about the data, right? Because this data point will also be going into the model as a numerical value, and this point as well. So it doesn't understand whether this was orange or blue. It just understands the number, right?
Yeah. Yeah.
And we
Yeah.
can see that it was now it became 4.5, right? And this is 1.6. So it was
Yeah.
previously 4. Let's see.
Yeah.
It was 4.5, right?
Yeah.
Just
Yeah.
4.5. Now we'll see how much time. So training loss is about 0, right? Now
Yeah. Close.
it is now 1.5 and this is minus zero point 0.3.
-3.
Yeah,
Huh.
0.39. No, 3.9, sorry. Now, if this one is now it became 4 point minus 4.1. The weight
It's
got updated,
increasing.
right?
Yeah.
Now, if we just go like the relation, the heavy relations are what? It is giving this layer equally information, right?
I think, yeah, almost equal.
Almost. Yes. 0.72, 0.80.
But in the ideal scenario, it's always not going to happen. When you
Sorry.
put the, but in ideal scenario, when you manually enter the real transactional that data, that
Uh-huh.
sometimes, yeah, it is not equally passing to everywhere.
Yeah,
Yeah.
that's true. That's what I'm gonna show, Abhi.
Mm.
I'll just increase the ratio to 80%, right? And I'll add a noise of 25.
Yeah,
And
noise will be always there.
I'll reduce the batch size, right? And now we'll see how it is performing. See, now the weights are getting updated very, very frequently. Like each data point, what each data point is doing, it is changing the weight very abruptly, right?
Due to the
And,
noise, right? Yeah.
yeah, and the batch size is 1, right? So each data point is having a very good impact over the weights and biases of it, right?
Yeah.
That's why
Yeah.
we see a very curvy training loss.
Yes.
It
Yes.
is not converging at all. And it
No,
will
I
even
can see that.
converge because the data noise is a lot, right? It won't fully converge. We have to, like, let's say, train test loss should be like 0.15 is okay for this kind of data, right? Because
Mhm.
the training loss and test loss is also relatable with the training.
What is the test loss? Do you know what is the test loss? Test
Yes,
loss.
test loss
Can
is
you-
actually ratio
Uh-huh.
of training to test data, right? So
Oh, how
ratio
many
of
times
training
you
data.
do the training? Okay.
So
Number of.
it is utilizing the data which is shown over here, right? It is 80%, right?
Hmm.
And
Huh.
it is keeping 20% of the data. Just have a look. I'll just undo it.
Oh, the okay. You first do the testing, then go for no train and test, right? Train and
Yes.
test. Yeah, yeah.
So see, have a look. If I just increase it, the data in this would increase. If I just make it 90, see, right?
Okay, got
And
it.
if we
Yeah.
just reduce so the data points would reduce,
Hmm.
right?
Hmm.
So Meanwhile, it is training as well and testing the output. Okay, I will reduce the noise to 10, right? And now let's see how it is performing. See, again, it is very, 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 very fast.
Kirby, yeah, yeah, very
Yeah. So
Kirby.
what we'll do, what should we do ideally now? Just tell me. I'll do whatever you say.
So here, can you change what generally do? Can we do the activation function?
Yes, that's a good choice. And what should we keep the activation function to?
Can we go for linear or relu? Anything is okay.
Okay.
And,
Actually,
uh,
linear is also ReLU is also a upgrade of linear, right?
linear only, yeah, yeah.
Yes.
But sometimes I have seen from my means, yeah, whenever I was testing, sometimes yeah, linear is better than actually
Yes.
yeah,
Yes.
yeah, relu. But I don't know why. But sometimes I have seen that it is actually working good. Means the output is coming nicely. Hmm.
Yeah, because why? Because of the range, Vibhu, because of the range. ReLU, what it does is it applies mod on the output,
Mod. Mm-hmm.
mod function. So what it does is it is actually mod of X. So it is keeping
Mod of
whatever the value is like in the positive value, right? It keeps it as it is. Like if the output was, let's say, 8, it keeps it 8. But if it was minus 8, it converts it into 0.
positive, right? Yeah.
Into 0. It will make any
Huh,
negative value to 0.
yeah,
So
yeah.
the range
Always
of
trying to
ReLU,
keep the positive. Yeah, yeah.
yes, the range of ReLU becomes 0 to max, right?
Yeah, 0 to yeah, 0 comma
Max.
3.4. Yeah, 0 comma 3 point. The max of 0 comma 3.2, right? Like that. That works.
No,
Yeah.
max value can be anything. Let's say, but max should be in positive.
Yeah.
So the
Mm-hmm.
out if suppose we are applying on a weight, let's say over here, right? If we are applying a weight over here, let's see, it is minus 0.33, right? This weight will become 0 in case of
0.
ReLU.
Yeah. Yeah.
Let's
Yeah.
see. This weight is not becoming 0 right now.
Let's give some time. Let's see. Maybe.
No, okay. Weight won't become 0, but the step size, because ReLU is an activation function, right? So weight initialization and training would actually get affected by that. Because what ReLU does is it uh, avoids what? Vanishing gradient descent problem, right?
Hmm.
So that the weight should never go like the weights need to get updated, right? If we are subtracting like from 0 something, right? It won't doesn't make sense, right? So
Yeah.
we
Yeah.
do not want a neuron to go dead. In that case, we apply ReLU.
Okay. So, uh, again, please come.
Okay, what is ReLU? ReLU is rectified linear unit. Yeah.
Uh, uh.
And the formula for that is that it makes the output range from 0 to max, 0 to x, whatever is the max value. Let's
So
suppose
that
the
means telling the neurons to stay active or keep
yes,
silent. Got the
yes,
point, right?
to
Yeah.
stay active so that the weight doesn't go. Like if we are just updating the weights, right?
Uh,
Updating the weights, if we are subtracting from a minus value a lot, right? A lot, a
yeah.
lot, a lot.
Yeah.
It doesn't
Mhm.
make a very huge difference because the value when we multiply it is already negative and it is not the weight is not getting updated very frequently. So it becomes very dead.
0.
It is not having a very good contribution in the network, right?
Uh-huh.
If the weights are not getting updated, suppose I'll just stop this, right? If I have this many hidden layers, right?
Uh-huh.
Suppose this this neuron, right, right there, needs weight updation. All the connection with this neuron and this neuron needs updation, right?
Yep.
But the weight of, let's say, this one is very, very less. So the value in the back propagation, W old is equal to what? W new minus learning rate times del L by del W old, right? So the
Mm-hmm.
weight, if the del O W, right, it is very low, very low. So the whole thing will just become very low and the weight will not get updated. The W old
Okay.
minus something, right? The minus
Uh-huh.
that value becomes very low, very, very low. The weight is not updating, getting updated at all.
It will be remain same, right?
Yeah. So
Nearly
that,
same. To
so
see.
the why we say vanishing gradient, because that gradient is the actual updation in the weight.
So it tries to make the gradient always one, right? If
It
I
tries to
recall,
make it always the max above zero, right? It
means they
doesn't
tell
want.
that always it should be one. Means they don't allow to get vanishing gradient descent, right?
No, ReLU is actually having a formula of 0 to max. Whatever is 0, max between 0 and x, it takes only the positive value. We can say that.
Yeah, yeah, yeah.
It only takes the positive value.
Yeah, if suppose -3, it will make it actually 0. If it is 8, it will take the
Yes,
8.
yes, yes. And in linear unit, it ranges from minus infinity to positive infinity. So
Yeah, yeah.
that is what behavior we are just trying to capture the linear relationship. It works with linear data. That's why, because whatever the data is, we are ready to accept that. Because if it is linear, other data points will also be following the same pattern, right?
Yes, yes.
So we in that case, taking linear is actually good.
Yeah. And we have something called it also you just actually mentioned, right, that ARLU helps to decrease or reduce the gradient vanishing that gradient. What exactly that you mean? I mean that it is always going to be one, right? For positive inputs.
Yes. No, not one. Suppose the value of x is 14, right?
Yeah.
So
Hmm.
if we apply value on that, so
Uh-huh.
whatever is max between 0 and the value of x will be the output. So in that case, it would be 14.
Okay, always the positive ones, right?
Yes, always the positive
Max
one.
max of the positive. Okay, okay. Uh,
So what is actually happening? If the action activation derivatives are very small, gradients will shrink layer by layer. If suppose if here only we are just getting gradient of 0.001, right? And we also need to update this one. Then what will happen? The gradient from each layer, right? Because let's say this is layer 1, layer 2, layer 3, layer 4, and layer 5. So
yeah.
del L by del W of this one, del L by W of this one, del L by W of this one into del L by W of this one. So if it is zero point 0.1, right? And it
Uh-huh.
is 0.02 and 0.01, 0.01. So if we multiply all this, like how much weight update would be happening here, right? It will be very,
Yeah.
very, very minimal.
Yes. Yeah.
So the training, the step, right? The step won't be happening a lot.
Okay. So
Will
that is going to be almost zero.
remember?
Yeah.
Yes, right? If we just have a look over here, right? This is let's say this is the nonlinear relationship, right?
Uh-huh.
And this is the global minima. And
Okay.
from here, where can I get those actions again? I don't know. Okay, no worries. Suppose
Yeah.
we are having on this one, right? From it was on at here, the minima was at here. The training loss was
Mm-hmm.
here something, right?
Mm-hmm.
And the
Mm-hmm.
training loss, if the model gets here, the weight, all the weights and biases get to a value, which is very optimal. The it will just come here, and the training loss will become zero, right?
Mm-hmm. Mm-hmm.
So what does gradient descent actually do? It does what steps forward when the it in the direction of global minima. Gradient,
Okay. Yeah.
this is a gradient, right? This is a
Yeah.
gradient.
Gradient.
And we are
Hmm.
what performing what? Descent. That's
Descent.
why
Yeah.
we
Yeah.
say gradient descent in the direction where the direction is in downward, right?
Oh, yeah.
Where the
Descent.
direction is downward. That means if it is downward, then it will be a very high chance that it is a global minima or minima at least, right? Local minima
Yeah.
can also be
Yeah.
there. And
Yeah.
that's where the optimizers help us in identifying whether this is the global minima or not. Okay, it will say,
Okay.
okay, this is we can see that the training loss is not reduced a lot, right? I
Uh-huh.
should increase the momentum and look forward to other directions, right? It will
Yeah.
change the course. It will come here. It will see, okay, I need to just go into the other direction. When the point comes here, right? It will
Yes. Yes.
see that, okay, I have momentum also has the direction. So it will, okay, I need to just go forward in the descent direction only
Yeah. So gradient descent means actually gradually descending the loss
towards
to
the,
make global minima.
yes,
Right? Yeah.
yes, correct.
Gradually that descending. Right. That's why they call,
Yes,
because the main goal of neuron, the deep learning main problem is the loss. Right? Because you
yes,
don't have, yeah. Because a lot of actual hidden layers. If somebody passing any that information, then you don't know whether the information you got from the previous uh, yeah, layer is the right weight and right
yes,
information, right?
yeah.
Yeah, we sometimes do write somebody's back, right? Then it is go another person. So same thing happens also in the neuron. That have you seen that clip anytime in the actually YouTube or somewhere? Everybody going and writing some information on the back of the other, and that goes to, and 10 people are on the line, right? So in this way,
Okay, it is called Chinese whisper, right?
yeah, child respect,
I
exactly, exactly.
actually I do make some informative videos. I did make a video on that as well, Chinese whisper. How does that work? And there we can
Yeah.
see the information loss when passing from one layer
Information
to another.
loss, yeah, yeah. So when it
Yes.
is passed from one layer to another or one person to another, it is
Mhm.
always there's a loss. And the gradient descent, because yeah, I remember that when I was taking the class, my professor gave that example long ago. So I remember that one that year. So the same thing happened when one information is passing from one layer to another. That time the loss happened, right? So how to minimize the loss? Then that's why gradually they're descending to get a global minima. So at that point, the loss is the minimum. Yeah,
Yes.
very least. You can actually add me, but what I am able to recall, I'm just trying to pass on you.
Yeah, that is very good actually. Actually, I can also understand what you just meant with Chinese whisper because you were just
Yeah.
indicating towards that. I think we have been like I have been following what you have followed in your early career, right?
Ah, yes, yes. No, but you may be knowing better than me because I don't use it on the day-to-day basis. But yeah, I know that yes, when the information pass, whether it's neuron or anything, they just
Yeah.
want to make sure that how much loss the information can be, how close
Yes.
accuracy that we can maintain. So that is the
Yes.
job of a gradient descent. Yeah.
Yes. Okay. Let's increase the if what will happen if we just increase the learning rate?
Yeah, just see that. If you add it, what is going to happen? Yeah.
Yeah.
Learning rate.
It is not learning at all, right?
Yeah. Yeah, it's
It is not
constant.
learning at all because there are a lot of weights to be trained, but the learning rate is so high that okay, it is nothing is happening. If I just what I just do is reduce the learning hidden layers, right? It will definitely do some action. Or no,
Yeah.
ReLU is not
But
making
still it
happen.
is nothing. Still
No,
nothing.
ReLU is because of ReLU, I think.
Oh, relu, relu.
Yeah. See, the learning rates, each weight is getting updated very at a very large rate, right?
Yeah.
And
So
it is
then,
not able to.
so then
Yeah.
the actually relu is good when there are more number of hidden layers.
Yes, yes.
Okay.
Because in a dense, you made a very fair point actually, Lulu. When we are having very dense layer, right? We are having, let's say, here we can have 6 layers, right?
Yeah.
Right. So in this scenario, this weight would be updated, like it will be what it will be. It will be the derivative of this into derivative of this into derivative of this into a derivative of this into a derivative of this, right?
Mm-hmm.
All
Mm.
multiplied together, and then it will get multiplied together with the learning rate, right?
Yeah.
So
Mm-hmm.
if it is actually very less, it is also very less. So it becomes very negligible for this. And this neurons weight end up into the problem of vanishing gradient descent. Vanishing gradient descent, like if we just go into back propagation, the gradient is actually getting vanished or very near to zero,
Mm.
right? That is
Mm-hmm.
why it is said it is vanishing. And what does vanishing gradient does? It just makes the neuron dead. It is
Yeah.
not having any information,
No,
right?
no, yeah, no information is passing. Yeah.
Yeah. So that is why. It is not learning any new data, so it is dead.
Yeah. That's not good actually. Yeah.
So was it a good thing to
Yeah.
just you got it right? Whole thing.
Yes, yes,
We
yes.
revise the forward propagation and the backward propagation, right?
I will do. I will do. Yeah, because now I think I need to go through if any notes or anything I have or any documents I have. I will definitely go through that. Yeah, we need to see that. Yeah,
It is important, right, Vibhu? It is very important
yeah, 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 yeah.
because
And
eventually
do you
we are
know
not
in
doing it day to day
when
life.
they go for when they go for this actually agentic AI and other thing, they also check for those interview questions. I'm just actually asking you. I don't know, but they
See,
go back to this
see,
kind of things.
I'll be very honest, right?
Mm.
If you're going into agentic AI, right, I'll be
Mm.
like focusing to just deliver the module in such a way that it is affecting your or improving your interviews,
In
right?
Hindu perspective also. Yeah, yeah, you
Yes,
are right.
I'm
Yes.
having that intention, right?
Mm-hmm.
And
Yeah.
I'll be covering the modules with that intent only, right? So what I have seen so far, right, when they are hiring any AI engineers or I am hiring an AI engineer, right? Then
Yeah.
what we actually try to understand is that the because AI is just like in today's word, agentic AI and all these things, RAG and fine tuning, all these are what buzzwords, right?
Yeah.
Because everyone can just Google what is agentic AI and they can teach, but that doesn't put them in the right position.
Right. Exactly. Exactly. Yeah.
That doesn't
Mm-hmm.
show confidence. The key to confidence in that is that you know how what it is actually and what is making it do some great things.
Yeah. No, no,
That
you are right. Yeah. Because if you don't know if you are
basics,
not able to recall or correlate the existing things, then the transformer architecture you cannot learn actually, because that is also based on the deep learning, right? So
yes.
you should know that how the transformer do and what is the behind the transformers, right?
Mm-hmm.
Yeah.
True.
Yeah.
So I'll just give you an example, right? I'll show you an example. This is my article actually, right?
Okay. It's in medium.
Yeah, it's on Medium.
What is
I'll
fine tune? Okay.
fine tuning of LLMs, right? For a
Mm-hmm.
business domain, right?
Mm.
So I'll just go down and just look at the training part,
Yeah.
right? We have data set, right? We have instruction, input, and output. Three layers.
Yeah.
Three
Mm-hmm.
informations are present in the data set, and we are converting it into a prompt, right? With the create prompt format, and we are getting the sample, right? It
Mm-hmm.
will be iterating over that. We are just identifying what is the model length, and because there is a limit on the input which we can give, right? And the output it can generate, right? So that we have
Yeah.
seen that from chat gpt 3.5 to now chat gpt 5.2 or o1 model, right? Or Gemini, they can
Yeah.
generate a massive content as compared to their previous versions, right?
Mm-hmm.
So sequence length, all these things. So if someone asks why, suppose it is a non-technical question. It will sound like a non-technical question, but it
Mm.
involves a lot of technical knowledge. Let's say I'll ask you, Vibhu, that okay, suppose you are given a task, right, where you have to generate, let's say, 30 pages of content,
Mm-hmm.
which needs to
Mm-hmm.
be in context, right? All the
Mm-hmm.
content needs to be in context, and the information which you will be utilizing should be coming from a provided set of 20 documents. Okay.
Yeah. Mm-hmm.
Suppose you have to write 30 pages of report and you are given 20 documents, right?
Yeah.
What would be your choice of model and why? See, it sounds very untechnical, right?
Yeah. Yeah. You don't know. Means I don't know what answer I can give because
Yeah.
I
So
can go
that's
for.
why we need to
Hmm.
understand what is actually sequence length, right? These things.
Hmm.
Getting my point?
Yeah. Yeah. Yeah.
So in just order to make your decision, you need to understand what is working under the hood for each model, right? And if it
Hmm.
is not possible, then how can you just break down the problem and get your work done? For that, also, you need to understand the limitations of the model,
Yeah. Yeah.
of the architecture.
Yeah.
Yeah.
Gemini versus ChatGPT, how they have done and what are the limitations.
Yes.
Yeah.
What are the different kind of models which we can go for? And why should we go for? Why not just stick to one model? Because ChatGPT can do a lot of tasks that Gemini can do. But why at some point of time we have to choose Gemini over ChatGPT or GPT models, right?
Or or Claude, yeah.
Yeah,
Anything
or
like that. Yeah.
Claude, Anthropic
Yeah.
models, or
Mm-hmm.
Grok.
No, I have never actually, honestly, I have never gone through Llama or any that all those things present, right? I have never gone through the know that all are actually that GPT models, but what are the architectural or functional that difference they have? Why sometimes they tell that yeah, Gemini performing well, not Chat GPT. In what scenario? What are the cases? Yeah, that's a good point. Actually, yeah, that's a very good point. Actually, we should
Yeah,
know that how those things are different.
we need
Yeah,
to understand the limitations, right? Then
yeah,
only
yep.
we will be able to save time. Like you are in a very senior position, right, Vibhu? And you
Mm-hmm.
need to be that level of confident and that level of vision you should have, that you are not making decision based on hit and trial, right? You already know what
Yeah, yeah.
will happen in the future if you just go with that, instead of wasting a sprint or a sprint of two, right? Or two is two to
Mm,
three sprints. We can just make a conclusion based on what I know, right? That it will
that's
save
true.
four sprint of time if we just go
No,
with this
absolutely.
LLM.
Yeah, yeah.
Yeah.
Absolutely. Yeah, yeah.
So I want to just develop that in you so that you are confident and also you can reason. Because just by saying something doesn't mean that you know. You also need to verify that, right?
Yeah, yeah. Absolutely. Yeah. No, no, I actually asked you, don't take it that I'm going to that way, but I just asked you how in India the interviews really go. Okay.
Uh-huh.
Yeah, yeah. So, no, what you told that makes sense. If you don't know the basics, you cannot jump into that one. These are high
Yeah,
level. Yeah.
exactly. Because like I have like took like not more, but I would have took like 60 to between 60 to 80 interviews so far now, right?
Hmm.
But in all those, what I just got to like hear was buzzwords, right? And why when I
Exactly.
just
Yeah.
say, like, why would you choose ReLU always? Or why does ReLU perform very well? Or for what problem does ReLU was ReLU introduced? Right? They have
Hmm.
no answer. ReLU
Yeah.
was introduced just to fix the problem of vanishing gradient. Just a single line, right? But
Hmm.
understand that you have it showcase that you have a very good understanding of what deep learning architecture is.
Exactly, yeah, yeah.
Yeah.
And actually, Relu compared to TANH or other thing, Relu has a very simple math, or
Yes,
Relu
very
is,
simple math.
yeah, simple math actually. It is just on
If it is
two,
less than
I think
zero,
just
it
say
is
that, yeah,
zero.
it is just above the linear one, right? So it has also very simple math, yeah.
Yeah, it is just like a rectifier. Rectifier, we are just rectifying the negative values and keeping the
Yeah,
positive ones,
yeah,
making the negative value zero, and we have rectified that part. It is just
yeah,
similar that we're just drawing a single line, and we have made this part as zero.
yeah, yeah.
That's it. And whatever max value is happening, it will always be max. Yeah.
That's true. Yeah.
So,
So it saves the vanishing gradient descent, right?
yeah,
Vanishing gradient, right? It saves.
yes. It saves the model. It saves the weights going into vanishing gradient descent.
Yeah, vanishing gradient descent. Yeah.
And similarly, there is a problem also called exploding gradient descent.
So that one I don't know. Okay,
Suppose
explode.
if the weight is in positive and the derivative is in positive, right?
Uh-huh.
And this derivative is also positive. This one is also positive. This one is also positive, and this one is also positive. Then what happens? Or suppose let's say two of them are negative and three of them are positive. So negative, negative, positive, 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 and positive. It becomes a very positive value, right? A bigger,
Yeah,
if we just keep on multiplying, it becomes a very bigger value.
yeah.
And we
Overfitting kind
do
of.
not know how many layers would there be, right?
Yeah, yeah.
So in that case, the weight updation for this one would be very, very much, right? It from
Yes.
positive it can directly go into negative, or from negative it can directly go into the positive. There is a very paradigm shift, right? So the
Yeah.
step size is very, very large. So if it is very large, in the next iteration, when the new data row would be given in, right, it will do just opposite thing, right? This
Mm-hmm.
will act just opposite, and when it will go forward, the training loss will again increase or just drop a lot, right?
Yeah,
And
yeah.
trading would become very unstable, right?
Exactly. Yeah, yeah. No,
Yeah.
generally I see. Actually, last time when I went for an interview, I think the same question they asked that what is the activation functions are there. I think, and he told that how the activation function is that differ from the gradient descent, something like that kind of interview question he asked
Activation
me.
function differ from gradient descent.
Gradient descent. How means people talk about a lot of things when it's coming to the deep learning. People always they told that actual activation function I changed, other things I changed, but
Yeah,
again they talk about
hyperparameter
gradient
tuning
descent.
actually it is.
Yeah, yeah. No, activation function generally tells that what the network is learning. Activation function, what it is learning, but gradient descent telling something like how it is
Making
learning.
the knowledge more accurate,
Yeah, yeah, yeah,
or
yeah. If
making
you
the
go
error
means
more like reducing the error.
yeah. Suppose I am telling that I am learning Python. So what I am learning, it is the role of activation that yes, I am learning something. But how I am actually learning, what kind of confidence I have, what kind of learning I have, the the depth of Python coming from actually your that from your gradient. That means what you are learning, those are all going to my brain. I'm not yeah,
Yes.
losing out. So he told he was a Bengali guy, very nice guy. He was told me, yeah, Vibhu, I know that you are telling, but the right answer is what and actually how. Okay.
Yes. So you can see the weight and biases update, right? This is the
1 minute.
rate, yeah.
Uh-huh,
And
uh-huh.
this is del loss by del W. So del W is the older weight, right? This is the older weight minus learning rate times del L by del W. It is for
Hmm.
layer. It is for just the first layer, right?
Yeah, yeah,
As we go into the depth, this it will get multiplied, right? Because it will be derived from the older weight. So
yeah.
if we just look here, what would be the older weight for this one? It will be from for
The
coming from
previous
this
one.
one. Yeah.
Yeah, yeah, yeah.
So this one becomes for it. If we just go forward, so it we have calculated the loss for this, and similarly for this. So this is del W1 by W2, del L by W1. This becomes del L by W1 into del L by W2. Similarly,
Hmm.
it becomes in a chain, right? And we need to calculate for each one. And this minus, if it becomes positive, very, very big positive, it creates a exploding gradient problem, right?
Yeah.
Is a very positive value. This also gets add up, positive one, minus and minus. So it becomes a becomes exploding
But
gradient. And
that kind of scenario is possible in the
yeah, it does happen
real life
sometimes.
data.
It does
Oh,
happen sometimes because if we
okay.
keep the learning rate a very high number, right? Let's say
Ah, yes,
it's 2,
yes.
it is 2, and this becomes a positive value or just negative value, right? It is negative and this is 2. So negative into negative, it becomes, sorry,
Big negative.
yeah,
But weight cannot be negative, right? Weight always. Oh, it may be. It
it
may.
can be negative as well,
Can
yeah.
be. Yeah, yeah, yeah. It can be because you may be learning Python, but you are comparing with SQL. So it
Yeah,
is not. Yeah, yeah. Means I'm just telling one example. Yeah, you are. Yeah, in the biology class, we are talking about mathematics. So that
yeah.
means you're completely in another domain or anything. So that you are learning is really negative here. Yeah. Hmm.
Okay.
Yeah, I have never
So,
experienced, but yeah, that can happen. Yeah.
yeah, it happens a lot less time, right?
Mm.
Suppose, let's say the derivative is just 1.1, right?
Yeah.
1.1 into 1.1 into, suppose all the derivatives are 1.1, right?
Yeah.
Suppose a scenario 1.1. If we just look 1, 2, 3, 4, 5, and 6, so it becomes 1 to the power 6, right?
Mm, yeah.
We are multiplying the same values, right? So it becomes
Yeah.
1.1 to the power 6. It becomes a good big value. If it was 1.5, it becomes even a big value. And suppose there were 100,
Yeah.
hidden layers, right? It becomes a very big value.
Yeah.
Can you imagine that?
Yes. Yes.
So it becomes very hard to keep the training stable in that scenarios.
Yeah.
So that's why we have two problems. We do not want the model to go into vanishing gradient problems as well, and or either the exploding gradient problem. That's why
Yeah.
we use batch normalization, layer normalizations, right? Or we just deactivate or freeze some of the weights, right? We have done that in CNN, right?
Yeah. 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 We also
Suppose,
do that very often. Yeah.
yeah,
Because we don't
suppose
want to
in
put
some
our.
layers we will activate and deactivate, let's say 20% of the layers, 20% of the neurons in each layer. Suppose when the batch size is 10 and it is iteration 1, this one and this one is freezed. No weight updation would be happening here.
Mm.
Similarly, in this one, or this one, or this one, the weights won't be getting updated. So what the model will do, it will use the other neurons in order to capture the same meaning, same relationship.
Mm.
So these will also get trained. So in this scenario, no particular or no individual neuron will get overtrained, right? There will be
Yeah.
a balance of neurons getting the information. Each neuron would be aware of it. So it becomes very good. Yeah,
Yep. Yep. You are right. Yeah.
makes sense?
Yep.
Okay, that's good. Yeah. Any questions so far now, Vibhu?
No. No. It's good. Thanks. It was very clear. Yeah.
Okay, I think we are good to go with the forward and the forward direction, right?
Yeah.
Okay. So let's
No, a lot of things actually. I have gone from my actual brain. You have thanks for refreshing out actually because I don't do deal with that day to day basis, right?
yeah.
So yeah,
Yeah,
a
yeah,
lot of
I
things
do
are gone.
understand. Even I don't do it on a day-to-day basis, but I'm glad that I get someone with whom I can just carry the whole topic and I can recall all the things. Even I don't remember a lot of things, but I'll try to just give my best over here so that you are aware of it.
Yeah.
Okay. Let's look at some. Let's look at deep learning architecture in a different way, right?
Yeah.
So deep learning architecture is what? It just an advanced version of machine learning, right?
Definitely. Yep. Mm-hmm.
And in machine learning, we need less data. Why? Because there is linear relation, and we just need to just iterate through all the points in order to come to a conclusive line which provides minimum loss for all the data points.
Yeah.
Yeah. That
Mm-hmm.
is why we need less data, because it has to, because even if we just give 90 rows of data, it will also give a line, right? If we give
Yeah.
1,000 rows, it will also give a line. There is nothing it can do because it cannot create a non-linear line or non-linear curve which can optimize or reduce the training loss to a very good extent.
Mm.
Got it?
Yeah.
But in case of deep learning, we have a flexibility to draw curves. And we can also say in machine learning, we are trying not to overfit, right? But in deep learning, we have an intent to overfit.
Yeah. Go as close as possible, right? So that's the goal. Yeah.
Yeah.
So that's what. Yeah.
Okay. So deep learning, like for how, what kind of task we can use deep learning for?
Deep learning, image classification one, right? That what we do
Yeah.
generally. Yeah. And deep learning, what you do, we can uh, have not done much actually on the deep learning side, if you see,
Mhm.
or we can go for something complex. Same thing, classification or complex prediction. But prediction, deep learning we can do use cases, deep learning use cases. Not sure actually. In the finance side, if you see, anomaly detection, one thing can be done, but
Okay.
that can be also done
Okay.
by
I'll
machine
have a question, Vibhu.
learning.
Suppose I give you a data set which is having both, like it is a data set, it has anomalies as well as the regular patterns, right?
Mm-hmm. Mm-hmm.
So how will you train a deep learning model, right? But you don't have a lot of anomalies there. You have some, but not a lot. And I want you to build a deep learning model which is able to capture the anomalies very well, like let's say 94% of accuracy. How will you do that? Just don't use the regular approach.
Okay, so you don't want me to use the machine
Regular
learning.
regular
I
thinking, like what
uh,
we use like regularly, or the standard one. I need you to think out of the box in that.
so you gave me a data set which having 94% accuracy.
I
Okay.
want 94%. Like I want a very accurate model, to be honest,
Uh,
because you won't be having a lot of anomalies, right? So
uh.
in
In
that,
this case, if you want very high accuracy, then the deep learning is better, right?
yeah.
Yeah. So mm, no, I didn't get your question. So you send me a data set
How
and
will
you
how
want.
what would be your process or thought process, and how to build the model, and how will you utilize it later on?
Okay.
Suppose you have
I will.
only 5% of, or let's say you are having a million rows of data, right? And you are having
Hmm.
only 400 rows of data which are having anomalies, but those anomalies are very clear and very, like the pattern is clear in that. How will you
Hmm.
do that?
So I can go to one of the model LSTM or something like that, and then do some predictions after
Hmm.
doing the EDA,
Okay.
and I can see that what are the my predictive models are actually that actually, yeah, that is going to give me. Then in this case, I can send you some sample output and tell that okay, the models has I have run
Okay.
through so and so models, and all means I may be compare going to two or three and tell that okay, these
Okay.
these are the models output. Then
Uh-huh.
uh, you can tell me to choose actually. So that's what we do in the real time scenario, right? We have the
Okay.
dashboard, we create all
Okay.
those outputs, and so that in the dashboard, so the business can see that okay. So
Yes, I got it. I got your point, Vibhu.
as your yeah, as your data changes,
Mm-hmm.
you may be means it may be that CNN is giving me best, but tomorrow LSTM giving me best. The
Let's
next
not
one,
decide on the model. We are
oh
having
okay,
deep
okay.
learning, which we can use any model, right?
Any model, yeah,
Actually,
yeah.
they are
Means I'm
there
just
are
telling
they
you
are just neurons, right?
exactly. End of the day, these are the neurons. Yeah,
And the strength lies in the number of hidden layers, right?
yeah,
And time and data type, right? So, okay,
yeah.
let's keep that aside. Correct me if I'm
Mhm,
wrong,
mhm,
right? I want you to just analyze what I'm saying, right? And just
mhm.
tell me whether will it be a good model or not. As I said that we are having a million rows, right? And
Yep.
we are having only 400 of the anomalies.
Yeah.
Yeah.
The
What I'll
ratio
do
is
is,
very small, right? Yeah.
what I'll do is, I'll drop the anomalies. Listen me, listen to me.
Uh-huh.
I'll
Uh-huh.
drop the
Uh-huh.
anomalies. I will clean the data. I'll only keep only that data, right? Which is actually what, let's say, which is into a very good quartile range, and it is not giving much of outliers, right?
Mm-hmm.
The
Mm-hmm.
actual outliers, I have just dropped it. And the difference between the actual outliers now, it because still there will be outliers, because if you just drop the outer outliers, right? If you just plot the quartile range again, there will be some outliers again, right?
True. Yeah. Mm-hmm.
Because the data will expand, right?
Yeah. Mm-hmm.
So the standard deviation would like expand a bit. So
Yeah.
the data points which were not previously outliers will become some outliers. So that is okay. But now my data set doesn't have any outliers, right?
Mm-hmm.
I'll make any column a target variable.
Any column. Yeah. Yeah.
Yeah.
Mm-hmm.
And now I will try to add more and more hidden layers, and I'll try to build a model which overfits this data.
Mm-hmm.
Got it?
Yeah. Yeah.
If I just overfit it and model got trained, the training loss would and test loss would be
Unless, right?
very less. Yes, right. It will be
Yeah.
because it has just overlearned that pattern.
Yeah.
Yeah. So the training loss and test loss would be very low. Now,
Mm.
if I just pass, I want this model. I have extracted the model, right, and saved it. And if I just give it the inputs of anomaly, right, and I'll just look at the training loss. Yeah.
Mm-hmm. Yep. Yep.
What would be the training loss?
Training loss will be also low, right?
Why? Because no, it will be high in case of anomaly. It has overlearned the true data, which is good data, right? Which is not having
Yeah.
anomaly. Suppose
Yeah.
I have just looked at the words good part, right? I have always
Yeah.
met kinder people, always throughout my life.
So
So
yeah, you
whenever
are
I
thinking
just
that all
come,
the people are kinder. Yeah. Yeah.
yeah, when I'll expect that person as kind as well, right? A new person. But when I
Mm.
meet, I'll say, no, get a very weird feeling from this one, right?
Yeah.
Because
Mm-hmm.
I got trained on the kinder ones. And now I got an anomaly. I will be able to identify that, okay, this is not the usual behavior that I have been seeing over past. So that will be indicated into the training loss, right?
Mm.
The training loss won't be accurate, won't be less for that particular case. Do I make sense?
So if the data is very predictable, then the training loss is going to be high. It will not learn anything, you mean to say?
No, if I just said that if we drop
Uh-huh.
anomalies, right,
Uh-huh.
clear
Uh-huh.
anomalies, then
Hmm.
the data is cleaned, right? It is
Yeah,
having
yeah.
no anomalies. And if I just overtrain a deep learning model on over that clean data, right, all the clean
Yeah.
cases, it
Uh-huh.
really understands and predicts well, and while also giving low training loss or test loss for the clean data
Mhm.
only, right?
Exactly. Yeah,
But
yeah.
as soon as it gets introduced with the anomaly, the training data
Hmm.
increases, right? So
Yeah, it will be high
training
loss.
loss,
Yeah,
yeah, training loss, test loss would increase,
exactly. Yeah, yeah, yeah.
and
Got it.
that you can use that as a predictor, right? Because you didn't
Yes.
had a lot of amount of data for the anomaly class.
Yeah.
Isn't that the smart way?
Yeah, yeah, yeah. So that's why he will learn something new, right? Because
Yeah.
yeah, yeah.
So it will say, okay, I haven't seen any relation like this. I need to update my weights, right? A lot
Yeah.
to adapt to
Hmm.
this kind of data. But we have already got the model, so we need not to train it. But we can use that limitation of just looking at the right data in order to predict the anomalies.
Yeah.
Yeah,
Yes, yes.
wasn't
You
that
are
cool?
right. Yeah. Yep, yep. Yeah.
Okay.
So he will get a big
Big
noise or
training,
big
yeah,
jump
big
there. Yeah,
noise, yeah, big jump
big noise. Yeah.
would be seen there,
Hmm.
right?
That's true. Yep, yep. No, that makes sense. Mhm.
Okay, Vibhu, so we have like passed around 1.5 year, right? One and a
Yeah,
half
yeah,
hour. So
yeah.
we
So
can
tomorrow, what I should be prepared for? Because today,
Vibhu, actually
really,
I
when
will
you
be
ask
traveling
me,
tomorrow night. I
okay,
will be in
okay,
bus tomorrow. So if you
okay.
want, we can do a class in morning. Like it won't be possible for you for the late night, right? Okay.
No,
Right?
morning is okay, but I just see actually lot of things I know, but I am not prepared that what we are going to start. So I was not able to answer many
Okay.
things. Okay, so
I
I
just
just
want
want.
you to just look at the deep learning part, basics,
Okay,
right?
I will definitely do
Rest,
that one.
rest, you can just leave it that to me. I'll help you with
Yeah,
that. But once you
uh,
are clear with the foundation, right, it will be much easier to go and work with, right?
yeah, yeah.
So
That's
just
that's
whatever
good.
we have gone so far, you will definitely be having a lot of doubts, right? A lot of queries. What would happen in that scenario? What would happen in such scenario? Why we are using this? Just clarify those things, or you can write them down, and we'll cover that in the next session.
Yeah.